All right, good morning, everyone. So today we'll talk about the sterilization tool, which is basically a lot of calculation. Let me see how many students we have right now. We have 26. Let me wait for another 1 minute before we start while I'm sharing my screen. Okay, 27. All right, let's get started. So first, before we start, I have a couple announcements. We have an assignment with the reading a material about retort processing. It was a study done by NASA about 10 years ago. They were trying to develop the space foods for the astronauts. So it's a very interesting study. So all the questions are related to that article. So the assignment will be due by the end of Sunday, this Sunday, basically. I'm trying to upload a rubric by the end of today. So before you submit your assignment, please check the rubric, make sure that you hit all the points. And another thing, good news is that I'm going to combine the lab 1 and lab 2 into one lab report because they are both related to sterilization, and one will be using the one that we just did was still retort, and this week we'll do a agitating retort. So basically they're the same concept but just different technology that we'll be using. So it will be better for us to put all the data together so the lab report can show more comparison between those two ways of doing sterilization. And the third is that I have created a discussion panel in the Canvas. So for the rest of this quarter, we'll be sharing this retort. We'll be sharing the data for the rest of all quarter in this panel. So if you can see my screen, if you click discussion, and in the lab data sharing, you'll see that I already posted the one thread here. So because every group will collect, so for example, last week, you guys have already collected some of the data, like the weight, like your thermocouple serial number. So the easy way to share your data is to reply with the attachment. For example, you can simply put your group number, for example, group 1, and then put an attachment here with a photo shot of your the data table. So it will be an easier way for us to keep track of all the data from different groups. And for me, I also shared the thermocouple data from here. As you can see, if you click the this link, it will direct you to the OneDrive. It will be shared OneDrive, where you can find all the experimental data. Let me know if you have problem accessing this folder, because previously when I share through Cal Poly OneDrive, there are always some students, they had trouble with the access. And if that's the case that keep occurring, I will repost them into somewhere else in the Canvas, so you can find it. Probably I will create a link here for you to access the data if that doesn't work for you. Any questions so far? So I'm hoping that each group can share your data as soon as possible. So it'll be easier for other groups to access the data and analyze early, because the lab report writing also takes some time. Okay, so that's the announcement. So today our class will be all about calculation, and I will use one data set that we collected from last Friday's lab as an example to show you how to analyze the retort data, the thermocouple data. Okay, so before we start, I'm going to quickly review what we have learned from last class about a few very important concepts, like what is less lethal rate. So basically, if you guys can recall, the lethal rate is the comparison um, between the temperature of retort and our reference temperature. For example, if our reference temperature is 250 degree F, and while we are processing at 230 degree F with a Z value of 18 degree F, we can calculate the lethal rate can we calculate in this equation to 0.077, which means at 230 degree F, the killing power is 7.7%. Right? So, which means 1 minute of processing at 230 degree F will be equivalent to 0.77 minutes at 250. Okay, so we'll be using this concept later in this class. So I'm just trying to quickly refresh your mind in case you forget about this concept. Okay. So another thing is the cumulative lethality, okay, which we also did a calculation. We actually worked with our group, and it was teamwork that we solved this problem, right? So finally, if we add all the lethality together, then we'll get a F0 value. Then we'll compare if this is has reached our required F0 value. So through that, we can determine whether our process has reached the safety standard, right? So what we have learned is basically we process a food product, then record its temperature at the cold point, and then we use based on this curve, and then we use all the lethal rate and all the intervals to calculate the lethality, the F0 value, and compare it to the required value to determine if we have reached the adequate thermal processing. This is what we have learned from past study, is to determine whether thermal process is safe or not, right? But what if we're trying to, what if our goal is determine the processing time, is design the retort process and determine the processing time, the back way. What can we do? So in that case, what we will learn today is that if we are given a one thermal process, it can be either over processed or under processed, and it will be given a random retort temperature, and we are given our required F0 value, and our goal is to determine the processing time. So the backwards is way much more complicated, okay? So the reason that we want our processing time to be just about right is that if we overprocess it, that will cause some a burning issue, right? And also the off flavor issue. But if we underprocess it, there will be some safety concern. So this processing time it just will help us to limit our F0 value to be rather close to the required F0 value. Otherwise, if we just by random trialing, for example, if here we process it for about 65 minutes, and we found that our F0 value is twice of the required value, but we don't know how much time that we should run instead to to reduce the F0 value to close to the standard value. So that's the problem. Okay, so I'm going to use one of our experimental data to show you how to do it. So first of all, we'll have to plot the processing curve. So for those of you, I'm hoping if you can, let me see. Do you guys all have Excel, right? Okay, excellent. And I assume that you guys know how to plot those curves. Do you know how to? Okay, I saw many people nodding head. So if you have problem of, do those data conversion, please let me know. Okay, so basically we're plotting it out. Use the temperature. Here is the degree axis because that's the unit we are given from the thermocouple, and the x-axis is the time. Okay, basically we started at about 9:57, 9:58, and then finished close to 11:30, 11:40-ish, right? So this is our processing time. So we have a heating temperature, heating up period, and we have a cooling down period. And this is the data recorded by the thermocouple. I don't know which group is that, but apparently looks like a green bean sample. Okay, so the first step is to plot out the temperature against the time uh, curve. Okay, so if you want to like if you have two screens, you can probably work on it in the meanwhile. Okay, so the second step is a little bit tricky. So remember the first step that we plotted out our y-axis is the processing temperature, okay? But in the second step, we need to convert the y-axis to become the temperature below the retort temperature, okay? So which means it's it's not the absolute temperature anymore, but instead it's the temperature difference between the sample temperature and the retort temperature. And here I'm using 123 just for demo here, because if you look at our table, the temperature goes to 120 something degrees C, which is 122.5 degrees C. So assume the retort temperature has to be a little bit higher than that, or there's something wrong with the calibration, but we have to use this number in order to make all the calculation make sense, right? Because although we know the standard temperature for retort is 121, but since our product reached 122 or higher, which means our retort temperature, there's some 1 or 2 degrees of error there. So I decided to set the retort temperature here as 123, just to show you as a demo, okay? So if we do the temperature conversion, okay, I think here has to be corrected. So if we have 120 degrees C, the temperature has to become 3 degrees C, because we are trying to show the temperature difference between the product and the retort temperature, right? Okay, and for example, 115 degrees C will be converted to 8 degrees C, because that's 8 degrees C below the 123, the retort temperature, right? So after we do that conversion, the second step is to convert the interval into the log interval, which means every one the major difference is 1 log. Okay, so for example, so if you look at this graph, what does that mean? If you see, for example, the green chart, the green plot started at 100, the 100 degrees C, which means it's 100 degrees C below the retort temperature, right? So which means it started at 23 degrees C, about the room temperature. So that's our refried bean sample, because we started at room temperature as a canned product, right? And for the green bean, the temperature is little bit lower, right? It's more than 100 degrees C, lower than the retort temperature, which is almost close to 0 degrees C. So this is what it means. So at time 0, it started here. So does that make sense, guys? Okay, let me know if you cannot, because here it's a little bit tricky. Uh, I can always talk a little bit lower or pull out the raw data for you to better understand.
So
Okay.
what is the dark blue line versus the teal line?
So okay, so there are two. So these are two products, Abby. The blue line is the green bean product, and the green line is our refried bean sample.
Okay. And so why is the Y interval going backward? Like it goes 100 to zero point 0.1 is higher.
Yeah, that's a typical way of doing it, and it sometimes it depends. Some people like to use, because in my case I like to show the same trend as our heating, and some people like to to use the backwards. For example, this was someone else. They plotted it in a backwards way. So that either way works as long as um, they are plotted in this way. I mean, it really depends on how people their I mean, they typically just follow one pattern. But I don't see any problem if we plotted from smaller number to larger number.
Okay. Thanks.
Okay, it won't impact the calculation results. Okay, so yeah, I'm more used to this way because it's more similar to our heating curve. Okay. So the smaller number means it's more close to the retort temperature. It's okay. So if you look at the holding period, the temperature is very close to the retort temperature. All right. So our starting time is 9:58 um, at 40 seconds because so our thermocouple recorded temperature every 10 seconds. Let me see if I can bring out. Okay. So here it is. Okay, so this is our raw data. Okay, and you can see that the here we have the timestamp, and here's the temperature recorded by the thermocouple. Okay, and you can see it's about 0 degrees C. Okay, it should be 0, but I think there's some calibration issue. Okay, because we immerse this data trace into water, so this should be 0. So that's why we can see our final temperature is a little bit off. Okay, so you can see we started heating, the temperature started increasing at 9:58. Okay, from from here you can see this heating started. Okay, and finally it reached 123 degrees C. Okay, so this can be either the retort temperature, the retort system is not stable, it might overheated, or either it can be due to the thermocouple calibration error. Okay, but in um, if the data is all accurate and everything is right, this shouldn't be 123. That's why I changed the retort temperature to 123 to make sure to make this calculation more reasonable. Okay, and so you can see we reached the highest temperature at 10:15 in the morning, and last and hold it for several times. Okay, and hold it for about 40 minutes, and started cooling. Okay, around the 11 11:23. Okay, and then this is a cooling down period. Okay, so that's how it so from the Excel sheet, basically you can determine where we started and how long we hold it and how long we use the retort process. Okay, so after that, will be, so after we convert this figure, we will be able to calculate the processing time. So the processing time we note as B value will be equal to this equation. Okay, this is a little bit uh, complicated equation, but we'll spend all our class today to try to solve this equation. So basically, if you look at each parameter means it, so the FH value, okay, the first parameter is the heating rate constant, which is the time for the heat penetration curve to cover one log cycle, okay. And I'll explain one by one and do the sample calculation using this green line later with you. So hopefully you'll have a better understanding. And the JH is the thermal lag factor, okay? And the IH is the difference between the retort temperature and the initial product temperature, okay? And the G value is more like a parameter that we'll find out from a table. But here's some physical mean, but sometimes it doesn't make too much sense. We have a table for you to look up for the G value. Okay, so the first one is, let's solve this JH first. So the JH value is the thermal lag factor found by extrapolating the curve. So if you look at the curve in the left, this is very similar to the curve that we have plotted. And you will see that at the very beginning, there's a like a very it's curving to a straight line, but there's something lag because once we are start heating the retort process, our product in the center, um, it takes some time for the heat to penetrate and actually reach the cold point. And so the thermal lag factor basically quantifies how long that takes, okay? Because once it reaches the center, it will start it will start a log, this straight line, which is more becoming a constant heating line. But before that, there was some slow, like a lag back. So basically, we are calculating this by comparing where the temperature the product actually started versus if there's no delay, where should the product start? Okay, so this is like a pseudo initial product temperature. Is that so theta PIH is the temperature that we assume we don't have any delay, then where should it started? Okay, so that's why there's a small gap between the actual starting time and our pseudo initial temperature starting time. And we use that as to compare to get our JH value, okay? So, and the same thing for the cooling as well, but I'm not to show you the cooling here because our data is not very good for calculating the cooling lag factor. So I'll just give you assign the number for your further calculation. But the JH here can be calculated in the product in the so theta R is the retort temperature minus the pseudo initial starting temperature here versus the retort temperature minus the initial product temperature. And by that, we can calculate how much lag was that at the very beginning. Okay. So this is a different people did it. So basically you can see the y-axis was kind of inverted, but if you, because this is calculating the ratio, so everything will be canceled out. And we are just reading the data. So it doesn't matter how you plot your figure. Okay. Any questions? Let me double check. Okay. Okay, so I'm using our refried bean sample as a example to show you how to calculate the thermal lag factor here. So in our case, you can see there was a straight line here, and basically we extrapolating the curve, and we will find the intersection with the y-axis, and it's somewhere close to 200, right? It probably can read here 100 here and 200, 300. So it's about 200, right? So that's our seat PIH, the pseudo initial starting temperature is 200 degrees C below our initial temperature, okay? So if you do a calculation, 200 below the initial retort temperature, which means the temperature difference between the retort temperature and the pseudo initial retort temperature is 200, okay? Because this plot shows the temperature difference between the product and the retort temperature. Okay, so that's why we can directly read this number, because the term that we use in the equation is the temperature difference, right? So for the product temperature, we can read it's 100 degrees C, right? We can read the theta R minus theta IH here is 100 degrees C. So the JH, the thermal lag factor, okay, will be simply 200 divided by 100 will be close to 2. Do you guys get it? Any questions? Okay. Okay, so this is the thermal lag factor. Okay, let me know if you don't understand. Let me see if I okay, no one talks in the chat box. Okay, so if you have any questions, you can let me know in the chat box as well. Okay, I'm trying to be very slow here because it's not easy to understand. Okay, so the second thing is the heating rate constant. Okay, so if you look at the definition, this FH is the time for the heat penetration curve to cover one log cycle. Okay, so what does it mean? Is that if you look our uh, graph, you'll see there's a region of our heating curve where was the straight line, right? Either in the green one, either in the blue line. There's almost a straight line, and the blue one is a little bit tricky because um, I think the sample here was this product, I guess it's the sample that we had our thermocouple dropped to the green bin because one of our group was placing the thermocouple on the top, and finally when they take it out, it was found that the thermocouple actually dropped. So that's why you see the curve actually is not very consistent. Okay, so I guess that's the sample that we had error with our data collection. But so we'll just discard. We'll use the refried bean sample as example because this is more like a normal heating and cooling curve. Okay, so if you look at here, the from the straight line we can find the one log reduction of the temperature difference. Basically, it's the one log reduction on the y-axis. Okay, so from here, uh, you can read here that it started from so because this is the Excel curve. So once we move our point on the curve, we can read those points, x, y values. And you can see that this is 29 minutes, 20 seconds. Okay, and we have our temperature difference 54.8. Okay, so that's a reading from y-axis. So 1 log reduction means this number will reduce to about 5.5, right? So we'll find another point in the later stage of the heating and make sure this is about 5.5. Okay, so the one that I found was 5.69. It's not like perfectly accurate, but it's about um, 10 times um, less. Okay, and basically we can subtract the time, the ending time by the starting time, which is about 50 minutes. So this distance, so we basically reduce the temperature difference from by 1 log, use the 15 minutes to achieve that. Okay, so this is the temperature, this is the time when we call it heating rate constant curve. So basically this is, uh, we found that uh, from this constant heating curve. Okay, so any questions about the how to find the FH value?
Yeah, I'm kind of like, it almost seems a little too simple. Like, I feel like I'm missing something.
Mhm.
So it's like, how did you decide to like for the green line, how did you
Mhm.
decide to end it there instead of ending it like at 14?
Um, so you mean this green line? How did I
Yeah.
decide how long is the process?
Yeah.
Okay, so this is a good question, Lauren. Actually, so you can pick your starting point um, um, at your favor. It doesn't matter where you start. For example, here I pick this point. Let me write it down. It's 29 minutes, and the temperature, the Y reading is 55.22, right? Okay, let me write it down here. So starting point, we chose 29 minutes, and the temperature difference was 55.22 degrees C. So that's our starting temperature, starting point, right? And so our ending um, temperature, we don't know what time, how much minute is that, but we know we're looking for somewhere close to 5.5 degrees C because that's the 1 log reduction, right? And so from this curve, we need to find um, how, what is time when the temperature reached the 5.5. And basically you can move your mouse here and see where was that. So at 112, it's 673, which is still not there yet. And let's keep moving, okay? And 114 minutes, not there yet, okay? And let's keep moving. Okay, here is 5.41. So this one is close, right? And let's keep moving a little bit to find a better spot. Okay. Okay, so this one is close. So this is one 1 hour, 16 minutes, and 40 seconds. And here we reach the temperature difference 5.57. Okay. So let's write it down. 1 hour, 16 minutes, 40 seconds. 1 hour, 16 minutes, and 40 seconds. And we reached our temperature difference 5.57 degrees C. Okay, so this is about 1 log reduction, right, of the temperature difference, and takes about 47 or 48 minutes, right? So that's why I put about it's 50 minutes here. Okay, so it's just easy for us to calculate. Okay, and in your calculation, you can use more accurate number. In our case, I'm just showing you a demo. Okay, so is that clear, guys? Any other questions? Okay, so this is the heating rate constant. Okay, 15 minutes. All right. So if we look back on our equation, the processing time, basically we already figured out the FH, right? Which is the heating rate constant. We found it's 15 minutes. And also we figured out our JH value, the thermal lag factor, right? Basically it's the, uh, we, we, we take the ratio between the pseudo initial product temperature and the initial product temperature. That's how we calculate JH, right? It's 2. And IH, this terminology here, is the temperature difference between the retort temperature and the initial product temperature. And we know retort temperature, 123 degrees C, and we know on our initial product temperature. So this is a known value, right? IH. And our last thing to calculate is the G value. Okay, and G is the parameter we'll find from table. It's the most tricky one. Okay, so first of all, let's look at the G value table. Okay, so this is a G value table from the textbook, and we'll use this for to find a approximate value. Okay, it's not accurate because it's based on two parameters. The first one is FH divided by U. The second one JC. So let me explain one by one. What are they? Okay. So first of all, I want to mention that G value is dependent on 4 different factors. The first one is the thermal death time, okay, and the second one is the slope, okay, FH, and the Z value as well. And finally, it's the temperature, the difference between the retort temperature and the temperature and of the cooling water, okay. So so, so JC here is the cooling rate constant, which I will give you a approximate number, and I won't let you to calculate because the calculation is very similar to the heating rate, to the heating lag, the JH value. The calculation basically is the same thing. We just extrapolating the curve and find out the ratio. Right? So I'll just give you a number for you to calculate. And here I'm just showing you how to calculate the FH divided by U. What is U? Actually, U is something we have learned before, but people are just using um, different letter to represent the same thing. Okay, so actually the U value is the thermal death time at a retort temperature. Okay, so this is the U value. Basically, we learned about this in our last lecture. Basically, for example, if we know that let's assume that we are processing it uh, at 121 degrees C for 7 minutes, our F0 value, our reference F value is 7 minutes, for example. And then we can calculate how long it takes at 123 degrees C using this equation, basically, because we know that at 123 degrees C, the killing power is 1.5 greater than the 121 degrees C. And then basically it means we only need 4.5 minutes of processing at 123 degrees C to be equivalent to 7 minutes at 121 degrees C. Okay, so not maybe a little bit slow down here. So does everyone understand what I mean? So basically, this is our assumption. First, let me state that. So this is all, for example, our requirement is 7 minutes at 121.1 degrees C, okay? But in our case, our retort temperature is 123. So in that case, actually we need less time, instead of 7 minutes, we only need 4.51 minutes, right? So this is the 4.51 minute is a U value, okay? I saw many people confusing. So this is one of the tricky part, but because it's when people develop this kind of standard table for everyone to look up, that was back to 1973, and all the letters they was not united very well. So some people use U value, some people use F value. So it's quite tricky if you look at those numbers. But in our case, you can just understand U value as the same as F value at 123 degrees C. Okay, and based on our lecture that we learned from the thermal processing principle, um, which is we calculated the lethality rate at 123 degrees C, it's 1.5, right? We can use this equation to get the lethality value. Probably, so we know that our temperature of the retort is 123, right? And our reference temperature is 121 degrees C. Okay. So if we plug in these numbers, we can calculate the U value. Okay. We can first of all, we can calculate the the lethality. It's 1.549, and based on that, so this is the ratio, okay, between the killing power of 121 degrees C and 123 degrees C. And based on that ratio, we can calculate the F123, okay? Any questions, guys?
Can you just go over really quickly how we're able to assume that the JC is 0.4 again?
Oh, that's a good question. Because in our case, so JC is actually we will calculate from this cooling rate curve, right? So because if you look at the definition, so these two numbers, these two parameters, they are actually the same. They are calculated in the same way. Okay. For example, JH is the thermal lag factor. Okay, we actually by extending the curve, and the JC is the cooling lag factor. It's also done by extrapolating the curve. But our problem is that if you look at the green line, green curve, actually our sample was not completely cooled even at the very end of our process. Basically, it's not completely cooled, but we just take it out. So the process is not 100% done. So in that case, we cannot calculate the cooling rate constant, the cooling lag rate, but I have to give you a assigned value for you to calculate. Okay, so this is just an assumption because our data does not support a reasonable calculation of that because our cooling is not done yet. Does that make sense, guys?
Yeah, that makes sense. Thank you.
Okay. Good question. Any other questions about how to find the U value and the U value here? Okay, good. Okay, let me make it a little bit clear. So when you guys do the calculation, you can probably follow the step by step. Okay, so this is how you calculate the U value. Okay, and once we get U value is 4.51 minutes, Then we can calculate the F divided by U value, the FU ratio, right? Because we already know that our F value is about 50 minutes, right? And our U value is 4.51 minutes. So the ratio is about 10.0. And if we go back to our table, we can find so first thing we locate our F divided by U here, 10.0. And then we use the cooling JC value. So basically we assign 0.4 here. So we can use 7.17. We can locate this number as our G value. Okay, so this is basically a table for you to find the G value. But in order to find this value, we have to do some calculation here. Okay. So finally, we got our G value, right? And then we can put everything back to our initial equation here. So we plug in FH, which is 50 minutes. Okay, and then we put in our JH value, which is 2 minutes, 2.0, and the IH 100. Okay, is the temperature between the retort temperature and the initial product temperature, which is 100 degrees C. And the G value, which we just found, was 7.17. And we'll find that the processing time is 72.3 minutes. Okay, so in our case, we actually processed it for almost 100 minutes. Okay, so this is like over processing. Okay, so if we remember that we set our F0 value is 7 minutes, but this is over processing. Okay, if we process it at this at 72.3 minutes, we'll reach a very close number to F0 value at 7 minutes. Okay, so this is like a back calculation. That's why it's way much more complicated. So, any questions about the processing time calculation? Okay, and the last step is the final adjustment by the come up time. So basically, this is the last step of doing it's a minor adjustment. Basically, it's assuming that the longer the come up time will impact how long we want to process data. For example, if the steam is not very efficient in heating up the retort, then probably our heating curve becomes quite different, right? So the come up time means the temperature for the retort to reach the set temperature, okay? So this is like a minor adjustment based on different system. And how we found that is that so this table was shared in the OneDrive that the link that I shared with you before in the Canvas. So this is our system, how they record the retort temperature, the system temperature by time. And if you look at here, we can see the red circle that I marked out is heating up, the come up period. Basically, you can see the temperature increase from 71 degree F to 250, okay? And this time shows the time elapsed. And you can see that it takes about 7 minutes, 28 seconds to reach 250.83 degree F, okay? So based on that, we can find that our come up time, CUT, it's close to 7.5 minutes, okay? And the last step is to do and based on that, we can do a adjusted processing temperature is equal to the B value, which we just got was 70 something minutes by that long equation. the minus 0.4 times cut, which is come up time, we can get our adjusted processing time should be 69.3 minutes. So this is a final final answer. Okay, so the final answer means in our system, we need to set the whole process to be 69.3 minutes to reach the optimal product, which is the product is safe, but with the minimal processing. Okay. So this is the final adjustment. It's based on, it's different, but it's just to correct different systems. Okay. If we run in a very different system, we have to change that number. So that's how we get everything step by step. Okay. So let's do a quick practice. And I just posted one question here from a textbook for you to practice. And there's no plotting, curve plotting. Basically, everything, every parameter is given. And what you need to do is to use everything that we have learned to solve this equation. Okay, so let's go through this question together. So we have a low acid food that is heated to at 115 degrees C using a process based on F reference F value. So this F value is at 121.1 degrees C, the same as us, and the Z value is 10 minutes. Sorry, 10 degrees C, and the F value is 7 minutes. Okay, the same as us. And the following information was obtained from the heating penetration data. Okay, so they just tell you what are each parameter instead of us. We look at every parameter by ourselves. Okay, so first one is the initial prod temperature is 78 degrees C. Okay, and the FH value is 20 minutes, which is the constant heating rate. Okay, the by one log reduction. Okay. And this is cooling lag ratio. The ratio of the cooling curve. Cooling curve is 1.8, and FC is 20 minutes. Okay, and this is the pseudo initial product temperature, 41 degrees C. Okay, and seat 774. Why are there two initial seat temperature? I think they're, okay, let's use 78, okay? So the retort takes 11 minutes to reach process temperature. And the question is calculate the processing time. So I'm giving you the question here, okay? So I'll give you about 5 minutes to think about it, and we'll go through the answers from the textbook together.
What was our initial retort temperature?
The initial, actually the initial retort temperature is typically not used in the equation. Normally I would say it's starting at room temperature because think about before heating, the retort temperature should be the room temperature, right?
Oh, so is our in the JH calculation, the retort temperature is the final retort temperature, which would be
Yes,
or
that's
115. Okay,
yeah.
thanks.
Yep, the theta R that we use is the final retort temperature, and you can see here it's 115 degrees C. Okay, that theta R is actually the constant. Let me mark it here. Yes, I misunderstood what you mean. This is the temperature. Guys, are you ready? I'm pretty sure it will take a longer time to calculate, but probably we should go through this together. So because you have the opportunity to practice with your group data, right? And you guys will work together to figure out um, what is your optimal processing time. Okay, so but I see many of you are still working, so probably I'll wait for another 30 seconds here before we go through the answer. Okay, so let's work on this together, okay? So if we look at this equation, we probably know that some of the parameter is already given, but some of them we're still missing, right? For example, the FH value is already given, right? It's 20 minutes. So this one is already given, but an IH value is also given, right? So basically that's the temperature difference between the initial product temperature and the retort temperature. So this is also given, right? But we don't know what is JH and what is G, okay? So, but we can calculate the JH using these three temperatures that are given, right? The pseudo initial temperature, the initial temperature, and the retort temperature. We can calculate that use those three values to calculate JH, right? And then for the G value, so if you look at the table for G value, we need a FH value, a VU value, and the JC value, right? So we need to use these three numbers to get our G value. So let's look at the JH first, okay? So basically our only unknowns are these two numbers, okay? So let's look at how we get these numbers. So the first thing is JH, basically that's the thermal lag factor, right? So since everything is given, since everything is given here, we can easily plug in the numbers. We can easily plug in those numbers to get our JH, the thermal lag factor, okay? And if you look at here, they use 74 degree F instead of 78 because I think there was some wrong with this question in the textbook. They give two initial product temperature. They assume you used one for the thermal lag factor and they use another one to calculate IH. But but in your case, either one used is fine. If you use 78, that's fine. Okay, so it's the final answer is close to 2.00. Even if you plug in 78, it should be close, right? It should be a little bit greater than 2, but it should be close. So that's our JH, right? Thermal lag factor we already got. And then the last one is the G value, okay? So so this is how they calculate IH, okay? And for G value, as I just mentioned, we need the F. If we look at the table of the G value, there's one parameter that is called FH divided by U, right? So the U here is basically the thermal death time at 115 degrees C, right? So basically we'll use the equation. Basically we'll use this equation to get our U value, right? So this was our something we learned before. So it's asking basically how long you need to process it at 115 degrees C in order to reach the equivalent killing power at 121 degrees C. So because here at 121 degrees C, it's 7 minutes. So at lower temperature, apparently it requires a little bit longer time, okay? So in that case, it's 28.59 minutes. Okay, so the ratio between the FH by U is 20 minutes divided by 28 minutes. It's 0.7. So that's the U value. Okay, and from the table that I showed you in the previous slides, since we know the ratio between FH and U is 0.7 and our cooling lag factor is 1.8, we can find our G value is 0.241 degrees C. Okay, so remember 0.7 and the 1.8. If we go back to that table, 0.7, okay, here. It's the F divided by the U value. And the 1.8 is our cooling lag factor. We can find that the G value is 0.241, okay? So and we can plug in the 0.241 into this equation and finally get the B value is, so the B value is before adjustment B value, okay? So it's for 49.6 minutes. And after the 11 minutes of cut adjustment, come up time adjustment, we got our final processing time is 45.2 minutes. Okay, so the final number means at 115 degrees C, we need to process this product for 45 minutes in this specific system in order to reach the 7 minute of reference F value. Okay, I know it's a little bit overwhelming. If you have any, if you're confused about anything, let me know. I think the only confusing part is the how to figure out the G value, right? This is the most tricky part. Other things is very straightforward, but this G value is the most tricky part because first you need to figure out what is the U value, right? And then figure out what is cooling cooling lag factor, JC. But typically this number is given in 99% of cases. This is given, okay? And from the table you'll be able to locate the G value. And once you have the G value, just plug it in, then everything should be fine.
I actually have a question on
Mhm.
calculating the U value.
Mhm.
I'm kind of confused where they got the 4.084.
Okay, so let's do this together, okay? So by the definition, we know that the U value is the thermal death time at 115 degrees C, right? So what we are given here is that we know that at 121 degrees C, our required minutes is 7 minutes. This is given by our question, right? This is our kind of reference F value. And we know that from the equation before, because at 115 degrees C, the killing power is not as good as 121 degrees C, right? So but the ratio, we can calculate the ratio. Basically, we did everything before. So basically, we want to calculate the ratio between the thermal death time, the killing power, and this was something that we have learned here, right? So here at different temperature, you guys calculate the lethality, right? Basically at different temperature, and so this was the equation basically we'll be using here. The lethality. Let me put back here. Okay, so we basically want to calculate the lethality at 115 degrees C. So what we do is just to plug in the numbers. Our temperature of running is 115 degrees C, and our reference temperature is 121.1 degrees C. Okay, and our Z value is 10 degrees C. So by this equation, what we are getting is the killing power at 115 degrees C compared to 121 degrees C. Does it make sense, Veronica? Okay, and let me do a quick calculation here. 115 minus 121.1, that's negative 6.1 divided by 10. Okay, and take a log times negative 0.1 is, so we get the killing power at 115 degrees C is 2.455. And this number means the killing power at 115 degrees C is 24.55% compared to 121.1 degrees C. So this was something that we reviewed at the very beginning of this class, right? Guys, is this understandable? Right. So in order to reach 7 minutes of processing at 121, we need more time, right? So basically we need how much time we need more is that we can divide by this number, because every 1 minute only equals to point. Okay, let me add one more sentence. 1 minute. So which means 1 minute of processing at 115 degrees C is only equivalent to 0.55 minutes at 121 degrees C. Okay, so in that case, we need 28 minutes to reach the same killing power. Okay, so this is the U value, how we get the U value. Okay, is that clear, guys? So I'll upload this updated slides for you to follow. Probably it'll be more helpful. Okay. Good. This is a very tough one. So initially okay, so before we finish this question, any other thing you guys are not clear about? Okay, so initially I wanted to put you guys into breakout room to try to process your own data from the Excel, but it seems we are running out of time. We can move this section to the next lecture on Thursday. So I will leave half of the class for every group to process your data. And if you have questions, just call me so I can help you with processing your data. And hopefully every group can get your data from the class. And after the Friday's class, we'll get another set of data. And for that set of data, I'll let every group to do that set of data by yourself, okay? So this is very practical skill if you work in a QA position in a company, that when you receive a thermocouple time log of the temperature and your supervisor asks you to calculate the optimal processing time, this is some calculation that you need to perform. I know it's very complicated, but otherwise you have to run it, for example, 30 minutes, 31 minutes, 32 minutes, trying to figure out what is the optimal time minute. So instead of trying again, this method gives you a approximation just to narrow down the range of that trying process. Okay, so that's why it's quite important, but it's very not easy calculation here. Okay. So that's it for today's class. For the lab report, since we are combining the lab report 1 and lab report 2 into one report, so the due date will be 3 weeks later. Let me see, 3 weeks. Yes, about 3 weeks later. And I'm going to post the rubric for the lab report by the end of this week. It'll be more clear with the grading. Okay, so any other questions before we finish today? If you don't 100% understand, that's okay. And next Thursday, we'll do everything in the breakout room. So there's definitely more time for you to get familiar with all this complicated stuff, okay? All right, sounds good. So I'm also available in my office hour too. So welcome to my office hour if you want to talk with me as well. Any questions before we finish? Okay, great. All right, thank you guys.
Thank you.
Thank you.